So last time we already reached this section. Okay, we already learned about the splitting and how to split the continuous value, how to split the categorical values. And you may guess that the problems will be like this one for the calculation for the paper-based exam. And we are going to learn more about the classification. There is one terminology, we call it overfitting. What does it mean by overfitting? And we call it overfitting because an industry may overfit the training data. Overfit. So if we know fit, fit means just okay, just enough. But if it is over, then it is more than fit. So the overfitting or more than fit, maybe it because of too many branches. So if the tree like this one, there are too many branches. So you may have like anomalies. Maybe it is due to noise or some outliers. Or maybe it is poor accuracy for unseen samples. So this is one example about the overfitting. Pet, chimney. So you do not want to buy this kind of pet because it is too specific. Only one person can sleep in this bed. You want to buy a general bed, so everyone can sleep on that bed. So we do not want this kind of overfitting. This kind of tree, we can say this is somehow overfitting, just based on the visualization. But later we will learn more about how we can verify the overfitting. So there are two approaches. So I just explained two basic approaches how to avoid overfitting. The first is pre-pruning. Prune. Do you know prune? It is to cut. It means we want to halt pre-construction. Halt pre-construction earlier. So we make some kind of condition. We make some kind of threshold value. So do not split a node if this would result in the goodness measure failing below a threshold. So if some values is below the threshold, then we do not put into the tree. But this pre-pruning is difficult because we need to choose the appropriate threshold. This pre-pruning, maybe we need to tune the single hyperparameter, or we need to tune multiple hyperparameters. So we will learn what is the parameter later. The other method is called post-pruning. Post. So if we have pre means before. Pre-pruning. So we want to cut before. But post means after. So after we have the tree, we want to cut. How to cut it? We can remove branches from a fully grown tree. So the fully grown tree means the complete tree, and get a sequence of progressively pruned trees. So we can try to cut, 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 cut until we get the good tree. So we can use a set of data different from the training data to decide which is the best pruned tree. But this one, it requires more computation than pre-pruning, but lead to a more reliable tree. So yeah, I can say this is cost complexity pruning, because you need to check which tree or which branches you need to cut. Some other technique is to create the ensembles. Maybe we will check it later. So this is an example. Let's say we have, this is the full grown tree. So from the previous one, we call this one as the fully grown tree. And if we look at this tree, the first attribute is A1. So this is the most important attribute. And then we check the A2, and then we have the A3, we have A4, we have A5. Okay, maybe based on this tree, we don't need to have this one. So maybe we need to just cut this one to make it simplified like this. How we can define this prune? For example, like this one. In the tree, there might be a sub-tree repetition. Let's say we have A1 is less than 60. A1 maybe about 8. We know the human age. We have a very high range, maybe from 0 until 100. But we do not have many people. We do not have many subjects. We don't have many person in our data. So the cut point is 60. And then if it is below 60, there's another cut point. There's another split point, 45. And then after we have this split point, after the algorithm check, again, there's another split point, 50. So it means the same variable happen in every of the node. So if this happens, we call this is repetition. So this kind of sub-tree repetition can cause the outfitting. So sometimes, we can cut. If we happen in like this one, we can cut in some section. Or there is another kind of problems, we call it replication. So replication means the duplicate subtrees exist within a tree. Let's say this one. I know the age, and if the age equal to youth, it goes here. If it is no, it goes here. So if the person is student, it goes here. If the person is not student, it goes here. So I put a box here to represent that this subtree is the same with this subtree. So these two subtree represent the same structure. So we call this is the subtree replication. So this subtree repetition and replication can impede the accuracy and comprehensibility of a decision tree. So sometimes, yeah, we can prove this kind of tree, or yeah, it depends on the data, how we need to deal with it. When we have the basic decision tree, what you already learned until now is based on the categorical data. If you want to enhance or if you want to improve the basic decision tree, yeah, we need to allow some continuous value attributes. The continuous value attributes will dynamically define new discrete value attributes that partition the continuous attribute value into discrete set of intervals. And if we want to enhance the basic decision tree, we need to handle missing attribute values. So if you include the missing values into the decision tree, yeah, it will give the basic decision tree result is poor. So we need to assign maybe the most common value of the attribute. So you already learned from the data preprocessing. Or you can assign the probability to each of the possible values. So it is to handle the missing values. Or sometimes you can also do attribute construction. So you can create a new attribute. If you create a new attribute, then you can avoid sparse. Do you know the meaning by sparse? Sparse means when you have a lot of data. If you still remember when we learned the association rule, we have bread and we have milk, or maybe we have like this one, almond. Only few people bought almond, but many people bought bread and milk. So we can see like this one is 1, 1, 1, 1, 1, 1, but this one might be 0, 0, 0. And then if we have another product, so 0, 0, 0, 0. So this is what we call as sparse. So if we have a lot of sparse like this, yeah, we can try to construct a new attribute. So the attribute constructor can reduce the fragmentation, it can reduce the repetition, and it can reduce the replication. So there are some other issues when we do the classification. It is the classical problem. The classification is the classical problem, extensively studied by statisticians and machine learning researchers. So we need to understand the scalability. Scalability means how we can use the data set with big data. This is, for example, million of examples. So million of examples mean the rows. Okay, we have a lot of rows and hundred of attributes. So it means we have a lot of columns. So the classification should be able to do with many rows and many columns. So why we need to understand this decision tree? First, because it is faster. So compared to the other algorithms, this algorithm is very fast compared to other classification methods. And then this decision tree is simple and easy to understand the classification rules. So you can interpret. Like what we already see from the decision tree, we can easily see that Okay, the most important attribute is in the top. And then the next, it will be the other attribute to give our decision. So it shows that it is simple and easy to understand. And we can use the query, SQL query for accessing the database with the decision tree. And there's also a comparable classification accuracy with other methods. So the decision tree is still relevant, even though maybe the accuracy is not that high, but it is still comparable. If you learn the data structure, okay, you may understand this graph. When the data items are getting more and more or bigger, so you need to find the algorithm that give you a relevant response time. If your algorithm can give O1, of course, that's the best. But it's impossible to find the algorithm with O1. Maybe your algorithm is ON or O log n. That's better. But if your algorithm is O to the power of n or exponential, this is very serious problem because it very costly. So we do not want to have this algorithm. Maybe we will check with this one or this one. This is still reasonable for the algorithm. So there are many other scalable decision tree induction methods. I do not want to discuss it now. So if you need to check those, this is the information. You can check Slick, or you can check the Sprint, or you can check the public, rainforest, and both. So let me just skip this part. If you want to study this one, you can take a look on the details. So what we learned from the first section, we know that our classification contains of two steps. The first step is we need to do the model construction. The model construction means we set the training set and then make the model. We call it, this is the model construction. And then after we have the model, we want to evaluate the model, or we call model usage. Okay. So those two we already learned from the first chapter in this slide. Model usage, or sometimes we call it the model evaluation. So we want to evaluate. We want to check whether the model is good or not. So usually when we are doing this kind of model evaluation, we will split the data. If we have the training set, if we have the data like this one, we can set 60-40. It means 60% for the training set and then 40% for the testing set. Or 70-30. 70% for the training set, 30% for the testing set. Or 80-20 or 90-10. It depends on the number of your data. So if your data is very huge, maybe you can consider 90-10. The higher the training set, of course, that's better. Now, we want to check the model that we already got. Let's say this is the decision tree. And you have the training data. So from this example, we know that we have, in our example before, we have 14 data. So we have 14 rows. We split it into the training data and the testing data. So I would like to use 70% from 14. Yeah, if you calculate, maybe it's not round up, maybe 10 something. So the result will be 10. The 10 data will be used for the training. And then the testing is the remaining. So we use 4 data. We can make the decision tree from this 10 data, and this is the decision tree. Now, I have this decision tree. I would like to test this decision tree with my testing set data. When we have 14 data, we know the actual decision. It means I know that this customer, he did not buy a computer. I know that this customer, he bought computer. I know that his customer, he bought computer. This customer, he bought computer. Okay. But what is the prediction result from this decision tree? So we need to check one by one. Okay, let's see. It is less than equal 30. Okay, the first is age, less than equal 30. Okay, in this case, we have the option less than equal 30 or 40. So yeah, we go to this one. And then check income equals to medium. Okay, income equals to medium. Okay, we go to this side. And what about the next? We can check the student. Okay, student fair, but okay, this is the attribute age. So age is less than 30. Okay, this will be the result. The decision is yes. So the prediction result is yes. But the actual result is no. Okay. Now let's check the second example. 31 under 40. When we check this 31 under 40, okay, it shows that yes. So the predicted result is yes. The actual is yes, and the predicted result is yes. What about the third example? Higher than 40. Higher than 40. Higher than 40, this one. And then next we check the income. The income is low, so it goes to this one. And then again, check based on the age. Age is higher than 40. Then the result is no. But the actual is yes. Again, the last one, yeah, we have the actual is yes, and the predicted result based on the decision tree is no. So from this one, we can make what we call as the confusion matrix. Okay, I will let you know later. But this one is the confusion matrix. If the actual is yes, how many predicted is yes? The actual is yes. There's only one which is yes. So we go this one. If the actual is yes, and how many the predicted equals to no? Yes, yes, no, no. So there are two. What about the no and yes? Okay, we have 1. What about no and no? We have 0. Okay. So once we have this matrix, we call this is the confusion matrix. The confusion matrix here is a useful tool for analyzing how well the classifier can recognize tuples of different classes. So the actual class, this is yes and no. I would like to know what is the result of the predicate. If the predicate is yes and the actual is yes, so we call it this is TP. What is TP? TP means true positive. If the actual is yes and the predicted class is no, so we call it this is FN. FN is false negative. If the actual is no and the predicted is yes, we call it FP. FP means false positive. If no and no, then it is TN. It is true negative. And we still have another which is called P and N. P means the positive and N means the negative. So when we have this confusion matrix, of course, we want to have a good model. So a good model means if we know that the actual is yes, the predicted should be yes. Okay. If we know that the actual is no, the predicted should be no. Then to understand the recognition, we need to get this number and this number. So the higher number on these two, it will give you more confidence that the model is good. If this number and this number is high, then it means your model is not good. So you can check that this recognition 95.42 it is the result from yes 96954 plus 2588 divided by 10,000 because the 10,000 is the all data. So let's get back here. Then what is the accuracy here? Or what is the total recognition here? We have 1 yes and yes, and we have 0 no and no. So it means we have 1 because this is the TP true positive and this is the TN, this is the true negative, and we want to check based on the overall data. What is the overall data? We have 1 2 3 4. So we have 4 data. Among 4 data, only 1 is true. Either it is true positive or it is true negative. Because we have only 1 among 4, then we call the accuracy is 25%. So we can get all the measures from here. if we call the accuracy or the recognition rate, we want to make this formula Tp plus Tn, that means the true positive plus Tn divided by P plus N, so divided by the total data. If we have the error rate or misclassification rate, means we will calculate this on the Fp plus Fn, Fp which is the false, Fn which is the false, divided by the total data, divided by P plus N. What is sensitivity or true positive rate, or sometimes we call it recall? It is the true positive divided by P. True positive divided by P. What is true negative rate? True negative rate means Tn divided by the total of N. Precision. So I want to know how big is the precision of the model. Then we can calculate the Tp divided by the Tp plus Fp, or we can just say that Tp divided by P prime. P prime is this one, the total of the predicted. Sometimes we need to check the F1 score or F score or F, harmonic mean, precision, and recall. So we will use this formula. 2 multiplied by precision. Precision is here. Recall is here. Divided by precision plus recall. So usually we will use this one if the data is not balanced. There's another measures, this one. Yeah, we need to determine the beta. So this is the formula. So yeah, you can see this one. For the model evaluation, we have the false negative. Yeah, we call this is the type 2 errors. And we have the false positive, or we call this is the type 1 error. So this is the summary. If you want to call the recall or the sensitivity, yeah, we have this formula. If we want to get the specificity, we call this formula. If you want to get the precision, you will get this formula. And the accuracy, you will do with this formula. Okay. So just a hint, there will be one question about this confusion matrix in your exam. When we do with the classification, it means we are dealing with the classification of the categorical data. Okay. The classification means the target is categorical data. As you might know, when we learn about the predictors, or yeah, we can have this as the regression, okay, or if you also learn about the forecasting later, we may need to have another evaluation method. So the predictor for the prediction and forecasting, the target is numerical data. So when it is the numerical data, we need to measure the predictor accuracy. It means it measures how far off the predicted value is from the actual known value. So we usually use the loss function. The loss function means we want to measure the error between yi and the predicted value yi prime. We call it the absolute error if it is just the subtraction yi minus the predicted values. We call it the square error if we make it the square. We have the absolute to make it not negative, or sometimes we make it square to eliminate the negative, and then at the end we will do the square root. So we can test the error, so we can make the generalization of the error by measuring the average. So if we have a lot of data, so we will check what is the error, what is the error, what is the error, what is the error, and then we will do the average. Mean absolute error means we will do the summation and then divide by the number of the data. If we want to make the relative, it means we will divide with the average or the deviation from the mean, the deviation from the average of the data. If it is mean square error, we will do the summation of this formula for all the data, and we will divide it with the number of the data. If we want to check the relative square error, it's the same formula, but we will divide with the error according to the average. So the mean square error exaggerates the presence of outliers. So popularly use square root mean square error, or similarly root relative square error. So after we have this mean absolute error, we can have the R. R means root. Oh, sorry, not this one. Mean square error. We have the root MSE. We call this is mean square error. Usually we call it this is MSE. We can make the square root. So that's named as the root mean square error, or we call RM, okay, RMSE. If we put the square root for this one. So the issues, if we are dealing with the classification or the prediction or regression, there will be issue about underfitting. So we already learned about the overfitting. Overfitting means the model is very good, but it cannot generalize. So if you still remember the pet example, if you want to buy pet, you do not want to buy pet that is very specific. You want to buy a very good pet that everyone can sleep in the bed. So this is also the same. You do not want to have the overfitting. The overfitting means like this one. The data is very, very good. The model is very, very good, so it can predict for every possible values. The model is very good, so it can classify every noise. It can be classified properly. So the red will be on the right, the blue will be on the left. So this is very good. So the line is very good. But there is a problem. We call this is the error. The error rate, if you use the training data, it will show very low error. Very low error means the model is very good. It can classify for every data. Maybe this is no and this is yes. So it's very good. But when you have a new data, because validation, the error rate is high. So if the gap is high like this one, we call this is overfitting. What about underfitting? The underfitting means when we have this error, okay, the training data is high error and the validation is also high. But what is the just right? We want to get the low error and we want to get the proper validation error. Okay, so this will be the difficult part of your task in your team project. If you are doing the classification, how we can find the just right model? We do not want to have the overfitting. We do not want to have the underfitting. We want to have only this just right model. Okay. I guess due to the time, let me stop here. So